So we will look at number 39. Know and understand what is meant by wavefront, coherence, path difference, superposition, interference, and phase. Okay, let's begin with a wavefront. Okay, so I am just going to draw this. You can just draw many of these. Each line symbolizes a wavefront. Now, what does this mean? How do we define a wavefront? A wavefront is a surface which is used to represent the points of a wave which have the same phase. So how do we look at this? Let's change this wavefront diagram into something like a 3D model, okay? Let's just make it look, sorry about that. Let's just go back. Yeah, let's make it look a little bit more 3D for easier demonstration. So we can draw that there. This is another one. And we can add many more. So as we can see, the crests of the waves have the same phase. These points, let me just use a laser to show you what points I mean. These points, they are all in phase, hence they will be represented by wavefronts like this. So by definition, a wavefront is a surface which is used to represent the points of a wave which are in phase. Okay, next we'll look at phase difference and path difference. We will look at that in a bit, okay? Let's start with what's the next one? Let's just check. So we have done, okay, wavefront is done. Let's look at coherence. Coherence is a term used to define two waves coherence is used to define two waves that have the same frequency and wavelength and have a similar phase difference, okay? So how do we define coherence? Coherence is when so more than two waves or two waves are, I made a mistake there. More than two waves have same frequency and are in phase. That is the simple definition of coherence, okay? So coherence is done. Let's hold path difference and phase difference. Let's look at superposition and interference. So superposition is when the displacements of two waves are combined. So the displacement, let me show you by example, okay? You have one wave like this. Amplitude is 1, okay? And you have another wave which is significantly more amplitude. So this will be, let's say, 2. When wave 1 and wave 2, so wave 1 and wave 2 interfere, they will superpose, and the resultant displacement is the vector sum of each wave's displacement. What do we mean by this? Let's draw them in the same diagram, okay? We'll use wave 1's illustration. So let's just draw wave 2 here, okay? It will look something like this, and the resulting wave will have a combined a vector sum of the amplitudes. So 2 plus 1 will give you 3, and your wave that you would have formed will be much larger than both waves, okay? This is just rough drawing, but yeah, trying to move as fast as possible, okay? What was the other one? Interference. Interference is used for a term to interference is what we talked about. When superposition occurs, interference also occurs. There are two types of interference. There is constructive and destructive, okay? So constructive interference is when the resulting wave produced by the two waves has a a greater amplitude than the other two waves, and destructive is when the resultant wave formed has a lower amplitude than the two waves that used it, okay? So constructive happens when the waves are in phase, and destructive happens when they are out of phase, okay? So how do we draw this? Constructive interference, CI, and destructive interference, DI. You will have a wave like this, and you will have another wave which will be in phase with this wave like this. So they will be in phase. And destructive interference, you will have one wave like this, and you will have another wave that goes anti-phase or out of phase to the original wave. So the resulting is a wave with a greater amplitude, and this one is a wave with a lower amplitude. That's constructive and destructive interference. Now let's look at the big ones. Path difference and phase difference. We can just take this one, okay? Be able to use a relationship between path difference and phase difference, okay? This is a bit important, so just keep in mind what is about to be shown, okay? You have a loudspeaker 1 and you have loudspeaker 2 placed at an angle, okay? Loudspeaker 1 has 1 wave, 2 wave, 3 wave. Loudspeaker 2 has, whoa, that was a mistake, sorry. Okay, loudspeaker 2 has 1, 2, 3, 4, okay? Just keep adding this. This is the 4th wave. I have to adjust the drawing, sorry guys. Yeah, so 1, 2, 3, and let's add a 4th wave here, okay? So at point, let's just make this point X. Loudspeaker 1 and loudspeaker 2 each release 4 waves, and they meet at point X. The part that they meet are at the same part of the wave, so we say that they are in phase because they are at the same point of the wave, both at this point here. And the path difference, so in phase, so phase difference is 0 degrees or 0 rate pi, whatever you want to call it, and the path difference is 0 wavelength, okay? Because the difference that the waves have traveled is 0. That's what path difference is. And phase difference is defined by how much of the wave lags behind another wave. Here, the wave does not lag behind the other wave, so we'll say it as that, okay? Now let's modify this and let's change this a little bit, okay? Let's add 1 wave here, 2 waves here, 3 waves here, and a 4th wave here, okay? So wave 1, sound speaker 1 has traveled 3 waves, while the other one has traveled 4 waves. They still meet at point X, which is this point here, so they are in phase, so phase difference of 0 degrees, but the path difference is lambda now, 1 wavelength. Why? Because sound speaker 2 produces a wave that moves an extra wavelength to the other sound speaker, okay? Say these waves meet at a different point. Let's just modify this a little bit, and let's say that these waves do not meet at that point. Rather, they meet at this point. So 1 wave, 2 waves. Oh, okay. 1 wave, 2 waves, 3 waves, and the 4th wave is a small part of the wave, okay? So wave 1, sound speaker 1, let's highlight this region, okay? It coincides with the other wave at this point, and the other wave coincides with this wave at the crest. So it's that part. The difference in phase here, from here to here, is half a wavelength. So we will use that to determine that, just keep in mind, if the difference is 1 wavelength between the points, then the phase difference is 0 degrees. But if it is half the wavelength, or 360 degrees. So 1, okay? If it is a half the wavelength, we'll divide by 2 and we will get 180 degrees. So the phase difference here, so phase diff is 180 degrees, okay? We need to know that. So essentially, when you're given these quantities, you should be able to turn them around to get what you intend on finding, okay? That's that. Let's just take that then. Let's move a bit more faster. Know what is meant by standing stationary wave, how the wave is formed, and identify nodes and antinodes. Okay. A standing wave or a stationary wave. So a stationary wave. A stationary wave is a wave formed by superposition of two waves traveling in opposite directions. Okay, what do you mean by this? You will have wave 1 moving like this and wave 2 moving like this in opposite directions, and they will interfere with each other to form a standing wave. How is a standing wave produced? You will have, we looked at this in the previous video, you will have 2 points like this, and you'll have a string. When you pull the string up, it will cause a wave to be formed. This wave will be reflected and it'll come back in that direction, and it'll just essentially form a stationary or a standing wave. These points of maximum amplitude or displacement are known as antinodes. The points of minimum of node displacement are known as nodes. Okay, that's antinodes and that's nodes. Let's just take that. Be able to use the equation V, speed of a transverse wave of a string. T is the tension, mu is the mass per unit length of the string, okay? How do we do this? You will have a pin here and a pulley over here. You'll have masses applied to the string. A stationary wave will be created here. Let's just draw that. And this is the stationary wave created. And essentially, you will have your velocity of the stationary wave be equal to root of tension. 1 second, guys. Root of tension over mu, where mu is your mass per unit length. Length is the distance from here to here, length. Mass is the mass, not the mass of this. Mass is the mass of the string itself, okay? Now, it is important to, mass per unit length will be constant. So if you have 1 meter of a string or 2 meters of the same material, your mu will be equal to each other, okay? 1 meter or 2 meter mu will be the same, okay? Tension is this force here in newtons. So that's how to find the velocity of a standing wave, okay? Take that. Lastly, we look at core practical 5, investigate the effects of length, tension, and mass per unit length on frequency of a vibrating string or wire. This is a practical and I'll give you all the details, but we have already drawn it here. So when you have a diagram like this, you'll be given an experiment. They will show you the steps of the experiment, and this experiment is self-explanatory. It'll come in the unit 3, not in unit 2, so we can just leave it here for now. Let's just take that. In the next video, we'll look at the remaining topics. Yeah.